Hi everyone, welcome to this new lecture of hydraulic machines. In this lecture, we discuss the concept of maximum speed of reciprocating pump during suction stroke and delivery strokes. So, in our previous lecture, we have discussed many concepts regarding the suction stroke and delivery strokes in the reciprocating pump, like the effect of acceleration, effect of friction in the suction pipe and delivery pipe. So, many things we have discussed. In this lecture, we discuss about the maximum speed of a reciprocating pump during the suction stroke and delivery strokes. So for this, I have taken this diagram. So before coming to the diagram, let me tell you that when the maximum speed occurs, or when we'll get the maximum speed of a reciprocating pump. So the maximum speed of a reciprocating pump can be determined from the pressure value. So pressure of what? The pressure in the cylinder. So the pressure which is present in the cylinder. So during the suction stroke and during the delivery strokes, this pressure of the cylinder, it should not be below than the vapor pressure of the liquid. Okay, that we need to remember. So the pressure which present in the cylinder, it should not be, let me write, it should not less than the first condition is there, the vapor pressure of liquid. The vapor pressure of liquid. So liquid of what? The liquid which is flowing through the suction pipe and through the delivery pipe. Okay. If suppose, this is the first one condition as I told you, that pressure in the cylinder should not be less than the vapor pressure of the liquid which is flowing through the pipe in the suction pipe in the delivery pipe, because suction stroke is during the when the fluid is flowing through the suction pipe. Delivery stroke will be when the fluid is coming out from the cylinder and is going out through the delivery pipe. At that time, delivery strokes will be there. So if suppose the pressure of the cylinder or the pressure in the cylinder is below or is less than the vapor pressure of the liquid, is below than the vapor pressure of the liquid, then what will happen? Then the dissolved gases which is present in the liquid, that will be liberated, and which will form, or that will form in form of cavitations. That means air bubbles will be formed from that liquid, and once air bubbles will be formed, then if this is the condition, then cavitation started here. Now here if you see, this is the region for cavitation. Okay, now next point is, you can say the continuous flow of the liquid cannot be exist, or it cannot be placed. That means that separation of liquids will be there. So separation of liquid, when it will take place, when there will be pressure difference will be there, then the separation of liquid will be takes place. That means the pressure at which separation takes place, that is called separation pressure. Okay, so again I'm telling you, we can say the continuous flow of the liquid does not exist or will not exist. Okay, that means the separation of liquid will takes place. This continuous flow will be not there because of the pressure difference. So if continuous flow is not there, then the pressure, the separation of liquid will be takes place in the sense. So the pressure at which point that separation started. So the pressure, I can say next one, the pressure at which separation takes place, that is called separation pressure. That is called separation pressure in the liquid. And the head which is corresponding to the separation pressure, that is called separation pressure head. The head which is corresponding or which is related to this separation, that at which point the separation pressure started, at what location, what is the distance from this point. So that is nothing but H, we can write this is a separation pressure head, and that is denoted by H separation. Okay, so this H separation for the liquid, or for the liquid means in the sense water. Okay, the value for the separation pressure head is, this is, we write here, the value for the H separation is 7.8. So 7.8 also, this is below than the atmosphere pressure head. Now if you see, this is our atmosphere pressure head. So from this point to this point, this is nothing but the center point of the cylinder. Okay, and from this center point of the cylinder to this label, this is sump label, this is our sump label, this is HS, suction head, and from this to this point, this is your delivery head. That means after here delivery pipe is there.
This is your HD. Okay, so what is saying here that edge separation, the value of 7.8, it is below than the atmosphere pressure head. So atmosphere pressure head value is 10.3. so we know that how to calculate this one. P equal to rho gh, and from this h we can write P by rho g. So this is from this value we can calculate. So P equal to the atmosphere pressure 1 bar we can consider by, this is the density 1000 into 9.81. If you find out, if you solve this, then we'll get the value. Already I told previously also. So this is the value of H atmosphere, that means atmosphere pressure head. So how much, if you subtract this value of H separation, that means 7.8. So how much we'll get? Like 2.5. So this much meter or this much height is there, and that is absolute pressure will be there. So see, separation may takes place, as I told you, that either in the suction stroke or either in the delivery strokes. So what is the maximum speed of the reciprocating pump during the suction stroke and the delivery strokes? Now we'll calculate about that one. So the first one I'll give the heading of, okay, so first point, let me write the maximum speed, during suction stroke. During suction stroke we can write. Okay, so to understand this one, we need to like look after to this diagram here. If you see this diagram, okay, the absolute pressure head. So the absolute pressure head during the suction stroke, as I told you, this at the up to this part we have suction stroke, and after this we have the delivery strokes here. This is our delivery stroke, this is our suction stroke side, and here at the y-axis we have the pressure head value. We have the pressure head value, and at the x-axis we have the stroke length. Okay, so stroke length is where inside the cylinder when the piston is moving from one side to other side, that is stroke length. And the crank angle, like how the crank is moving, so there also we can get it. Anyway, so suction head here, delivery stroke is here, and as I told you, this is our suction head, this is delivery head. Along with this is HAS. HAS is nothing but that head due to acceleration, the pressure head due to acceleration at the suction pipe. Similarly here, the pressure head at this delivery pipe due to acceleration. Okay, now this is HFS. So this, about this diagram already I have discussed in a previous lecture. Okay, so this diagram, this box is, if you say A, B, C, D, this is for the ideal indicator diagram. Okay, now if I consider A dash, B dash, C dash, D dash, only this one, then that is the effect of acceleration, in the pressure suction pipe and delivery pipe. Which one? A dash, B dash, C dash, D dash, this line. Okay, first one what I told you, A, B, C, D, that is ideal indicator diagram. Okay, second one is effect of acceleration in the suction pipe and delivery pipe. Now if I say A dash, B dash, C dash, like A dash, G, B, like from here to we need to consider A dash, G, B dash, C dash, H, then D dash. If I consider this one, then their effect of friction as well as acceleration both are there. Only if I say this one, then that is different. So that already we have discussed previously. So here what I need to consider, so here what I can say, that the absolute pressure during the suction stroke, so that is minimum at the beginning of the stroke. So beginning of the stroke means at this point, if you see, that is our beginning of the stroke. So the separation can take place at the beginning of the suction stroke only, that at this point. Okay, so at this point the absolute pressure of the head in the cylinder, okay, at the beginning of the stroke, that will be equal to the H separation. Okay, so what I can say, H separation we can write here, H separation we can write here, what is the H ATM, that means what is the atmospheric pressure, and this minus, so HS suction head plus HAS, this one. Suppose if I consider this one or below to this one also, okay, the separation can be taken any places. So for this condition, what we have considered, the absolute pressure head in the cylinder, at the beginning of the stroke, that will be equal to the separation pressure head. So what I can write, H separation equal to atmosphere pressure head minus HS plus HAS, and this is absolute we can say. So from this form we can, what I can write here,
I can find out the value of HAS. Okay, so let's write down from here. HAS equal to, we can write HATM minus HAS minus H separation. Okay, this is the value. Now here if you see the value of H separation and the value of suction head, the value of H separation and the value of H suction head, okay, mostly it will be given. If it is given, then we can calculate the H separation from that. So HAS we can calculate by using this formula. Okay, because this value is known and this value is given, or this value is given, means we can calculate easily the HAS value. Okay, so this is the pressure head due to acceleration at the suction pipe. Okay, now we know that one formula, just I'll change it. We know that HAS formula, let me write here. So HAS equal to, we have seen previously, this is acceleration due to the pressure head at the suction pipes, that is LSG into A by AS into omega square R. Okay, so the beginning of the stroke theta will be 0 degree. So at the time cos 0 will be like that will be cos 0. So cos 0 in the sense that will be 1. Okay, so here we'll get this equation. Now this is, suppose one equation, give it equation number 1, and this one give it equation number 2. Now if you see these two equations, then what we can write from here, okay, we can write HATM. Okay, or else what I'll do here, I'll put this value of this HS in this like in this equation, this two equation, what I'll get finally, I'll write HATM minus HS, and this is minus H separation, correct, H separation, then HS value I'll put this equation. Okay, now LS by G into A by AS into omega square. Now this is our equation. Now in this equation, if you see, this is equation number 3. So in this equation number 3, if you see the equation, that value of omega is there, the value of omega is there. So from this equation, the value of omega, or nothing but the speed, that can be calculated, omega, or we can say the speed. Okay, from omega is given, from that we can calculate the speed. So this speed is the maximum speed of the reciprocating pump without separation during the suction stroke, without any separation during the suction stroke. Because again, one more formula, we know that omega equal to 2 pi n by 60. From this we can calculate the maximum speed. This is for the first condition. Second condition is, what? Second condition, similarly we can write that maximum speed during delivery stroke. Similar concept will be taken for this also, like during the delivery strokes. Okay, this is our delivery strokes time. Okay, now once you started from here, delivery stroke started. So what is the probability of separation of pressure will be there? So during the delivery strokes, the probability of separation can be possible at the end of the delivery strokes, at the end of the delivery stroke, at this point. Like this is the starting of the delivery stroke, this is the end of the delivery strokes. If you consider the effect of friction, effect of acceleration, then both all will be concept will come. So the pressure head at the cylinder at the end of the delivery strokes, that can be written, how much we can write? So total how much is there? HATM plus HD, HATM plus this HD, okay, minus this HAD. So at the end of this suction stroke normal, if I take, this will be end. Now here what I can write, so okay, let me write, this is HATM plus HD minus HAD, and this is our absolute, this much meter. Okay, if the separation can be avoided, or if the separation is not considered above the pressure head, should be more than the separation pressure. So that means, so what I mean to say, if separation is to be avoided, the above pressure condition or this pressure condition, we can write, okay, it should be more than the separation pressure head. So for limiting the cases, we can say that H separation, for limiting the cases, H separation, we can write HATM plus HD. What is there? Let's write it. Minus, and write HAT. Okay, this one we can write. Or similarly, we can write HAD acceleration. The pressure head is due to the acceleration at the delivery pipe. This one we can write HATM minus HD minus H separation. Okay. So, but you can see the HAD, the pressure head due to the acceleration at the end of the delivery strokes, it can be written similarly. What I have written here, this one, similar way I can write here HAD. So HAD equal to LD by G into A by AD, and this is omega square. Okay, now if I see again same thing, I'll write here on in this value. I'll just put this value here. That means LD by G into A by AS into omega square equal to, you can write HATM plus HD. The same equation just I'll write here. This is plus, not minus. This one minus. This minus H separation. Okay, this is the equation. Now here also, if you see this equation, we have the option of omega. So let's give this equation number, suppose 4 here. Okay, so in this equation number 4, the value of omega, see, the value of omega can be identified, and from this we can calculate the value of speed. So this is the maximum speed of the reciprocating pump without any separation during the delivery strokes in the pipe. Okay, so these are the two equations. From this we can calculate it. I hope you understand. Now one more point I'll tell you, that during the suction stroke, as I told you that this separation can be takes place at the suction stroke as well as in the delivery strokes. Now the maximum speed during the suction stroke can be like it should not be below than the vapor pressure of the liquid. If it is there, then cavitation forms. Now suppose one more option I'll tell you. Okay, during the suction pressure, okay, during the suction pressure, suppose it drops than the atmosphere pressure head. Okay, like when the maximum speed can be considered when our cylinder pressure will be less than the atmosphere pressure, then the pump started rotating. But if the pump is it is rotating with too high, if the pump is rotating with too high speed, the pump is rotating with too high, then what will happen? At that point, our acceleration head will be increased. Our acceleration head will be increased. Along with that, the friction loss during the pipe, the friction head loss also increased here. Okay, similarly, along with that, the cylinder pressure will be like it will be reduced than the vapor pressure. Again, if the pressure in the cylinder is reduced than the vapor pressure of the liquid, then cavitation forms. Okay, or that means separation forms. So next one we can write the cylinder pressure falls below than vapor pressure of liquid. If this happened, then our cavitation started or separation started here. Okay, separation started here. The same thing what I have explained here, just I have written in this these four lines. So how to avoid this? How to avoid these conditions? And for that, I can write one equation: HATM minus HAS minus HAS minus HFS. It should be greater than equal to HV, whatever it may be. We need to satisfy this condition. So here HATM equal to atmosphere pressure head. Similarly, this is suction head, and this is that we know that acceleration, that head due to the acceleration at the suction pipe is the effect of friction or head loss due to friction at the suction pipe. It should, all these things should be, all these values should be greater than the HP value. So this is nothing but the vapor pressure head. Okay, this is the vapor pressure. Anyway, so I hope you understand this lecture. Still, if you're having any doubt and query regarding this, you can give a comment in the comment box.